Good morning, everyone. Today I am going to present the topic Diffie Hellman key exchange, which is an important concept in public key cryptography and secure communication. Diffie Hellman is a cryptographic method. The Diffie Hellman algorithm was proposed in 1976 by Whitfield Diffie and Martin Hellman. It was one of the first practical methods for secure key exchange over public networks. The main purpose of this method is to allow two users to establish a shared secret key without directly sending the key over the network. This idea revolutionized computer security and is now widely used in many commercial security products and internet protocols. Diffie-Hellman works. Diffie-Hellman works as a public key distribution scheme. It allows two users to create a shared secret key which only the communicating participants know. However, Diffie-Hellman itself cannot directly encrypt messages. Instead, it is used to securely generate a key that can later be used in symmetric encryption algorithms. The algorithm is based on mathematical operations in finite fields, especially exponentiation modulo a large prime number. Its security comes from the discrete logarithm problem. While it is easy to compute exponentiation modulo a prime number, it is extremely difficult to reverse the process and find the exponent. This computational difficulty ensures the security of the key exchange. Setting up the parameters. Before starting the key exchange, both users must agree on some public parameters. First, all users agree on a large prime number q and a primitive root a modulo q. These values are public and known to everyone. Next, each user generates their private key. For example, Alice chooses a secret number called XA, which must be less than q. Then each user computes their public key using the formula YA equals A to the power of XA mod q. Finally, these public keys are shared openly with the other participant. Even though the public keys are transmitted over the network, the private keys remain secret. Key exchange mechanism. Once the public keys are exchanged, both users can compute the shared session key. Bob computes the key using Alice's public key and his private key using the formula KAB equals YA to the power of XB mod Q. Similarly, Alice computes the key using Bob's public key and her private key using the formula KAB equals YB to the power of XA mod Q. Even though the calculations are different, both users arrive at exactly the same secret key. This shared key is then used for symmetric encryption, allowing secure communication between Alice and Bob. An attacker who intercepts the public keys cannot easily determine the private keys because it would require solving the discrete logarithm problem, which is computationally difficult. Working example. Let us look at a simple example to understand the process. First, both users agree on public parameters. Prime number q equals 353 and primitive root a equals 3. Next, Alice chooses her private key XA equals 97 and Bob chooses XB equals 233. They compute their public keys. Alice calculates YA equals 3 to the power of 97 mod 353 equals 40. Bob calculates YB equals 3 to the power of 233 mod 353 equals 248. After exchanging public keys, they compute the shared key. Alice computes 248 to the power of 97 mod 353, and Bob computes 40 to the power of 233 mod 353. Both calculations produce the same result. Shared secret key equals 160. Man-in-the-middle attack. A major vulnerability in Diffie-Hellman is the man-in-the-middle attack. In this attack, an attacker intercepts the communication between Alice and Bob. The attacker creates two separate key pairs and sends his own public key to both participants, while pretending to be the other person. As a result, Alice unknowingly shares a key with the attacker, and Bob also shares a different key with the attacker. The attacker can then decrypt messages from Alice, read them, re-encrypt them, and send them to Bob, making the communication appear normal. To prevent this attack, Diffie Hellman must be combined with authentication mechanisms such as digital signatures or certificates.